Okay, let's start. So today is your time. My plan, I'll say a little bit about the exam, not a lot, but the plan today is I'll answer questions for as long as you have them or until 2 hours is up, whatever comes first. So that's the plan for today. It's review, whatever you want me to review. And you get to guide it. The exam, 2-hour exam, we've had 2 hours all the time here. So I don't expect the format to be much different than the last test has been. One thing I'll point out about the last test, I've been telling people in my office who come and say, how can I do well? Every single question was what? It was cut and paste without any changes whatsoever from the homework to the review questions. Now, I can't guarantee that's going to happen because the first part of the course, the questions weren't very oriented to the lectures as much. The second part, I pretty much asked a question that everything I thought was important. And so once I started writing the homeworks, I think they're a pretty good indication of what I want you to know, what you ought to review, and that sort of thing. I might combine questions, I might throw a little twist in, but the idea is if you know those questions, if you know that stuff, that material, you ought to be in great shape for the exam. You shouldn't have any trouble passing it, and all those sorts of things. Now, what happens sometimes is that people write down the answers, think they know the questions, and they're wrong. And so if you have any uncertainties, you want to get to my office and check. It's really hard to do by email, but I'll be there in my normal office hours, and I'm willing to meet people outside office hours. So the very first thing I'd suggest doing is know the answers to all the questions that I posted. That's certainly going to be helpful. I followed the book really close for the most part. Deviated a couple of times, like we did policy effectiveness. That's not in the book at all. And there may have been 1 or 2 other topics like that. But for the most part, the lectures track the book identically. And of course, you can always fill in from the lecture. So the answer to every one of the review questions is on the videos and in the book, except the few that I did myself. So, answering them shouldn't be hard. You should be able to watch the videos. They should be in the same order. Just go through, okay, there's that answer, there's that answer, there's that answer, and the same with the book. So, I'm not going to post answers to the review questions because I don't want you just memorizing the answers and not really understanding them. So I put graphs up because, oh, this shifts this way. If I get this question, I do this. Something really good at memorizing, but I never really get it. And so the learning part for me in the last section is either doing the homeworks before the answers were posted or working up review questions yourself. That's where the real learning is. And the exam is just to see if you learn all these questions. And so that's how I'm approaching this. So the question is cumulative. Will the questions be uniformly distributed over the material, or will it be weighted in any way towards the end? There may be slight weighting towards the end, but I will design it so that you cannot avoid the comprehensive nature. If I were to give you choice, I might say choose one of these questions and do all of these, something like that, so I can make sure that it's comprehensive. So it is comprehensive, but it could be weighted towards the end. But I don't want anyone to think they can just study the last material and not put any time in the earlier stuff and necessarily, I am not going to give the exact number because it will depend upon, but what I'm trying to give you a big clue in saying that I had exactly 2 hours. We've had 2 hours all along. If I think they're short questions, I might go all 6. I might give you choice. I don't know. But it'll be roughly the same kind of format that we've seen. I'm not going to promise there'll be choice. It depends on how hard I think it is. I thought the last test was really hard and that people just did really well. So you're smarter than I thought you were. You're learning more than I thought you were. So that's good.
Are you in your office tomorrow?
Well, tomorrow, let's see. I've got a seminar at 10:30 to 12. One of my PhD students is giving his job talks. I have to be there. I'm going on Reuters TV at 12:15. So I should be back in my office for part of the afternoon. I've got to collect a bunch of homeworks at 4 o'clock. It's somewhere in the 1 to 4 region. If someone sent me an email, I'd be willing to meet them. I don't know, I'll be in and out. Their Christmas party starts at 5, so I'm probably not going to be there much past 4 o'clock. So that's my plan for tomorrow. And I'll be there Monday, normal office hours for sure. And I'm really nervous about it. So, it's a live interview on TV, isn't it? This suck. Anyway, that's the plan. Wednesday at 1 o'clock, is that what we all think? In here. You're probably going to start asking me questions I told you need to know. So what do you want to know about?
Can you do a how the seed consumption, the slope of the IS curve in relation to the sensitivity of consumption to the, is it the interest rate, I think? That interest rate? Consumption, I wanted to know what, because I think it's a little different, if you shift it up or something.
All right. So I think the question is, how does the slope of the IS curve vary with a change in the MPC and the change in the responsiveness of investment to the interest rate?
Yeah.
So when we did the IS curve, it's y equals c of y minus t plus I and y.
So I'm talking about C of Y minus T.
Right. So c of y minus t is the MPC, or the responsiveness of consumption to disposable income, which is y minus t. So one way to do this is just say to yourself, okay, the slope of the IS curve is when the interest rate goes down, investment goes up, and that causes output to go up, right? So that's, and we didn't have an I here in our model, did we? No. What class that was? Anyway, so this is the slope of the IS curve essentially, intuitively. This is the I of I term right here. How much investment responds to the interest rate. And this is the multiplier. You've got a change in expenditures causing a change in output. What happens is the multiplier is 1 over 1 minus c of y minus t for this case. When c of y minus t goes up, the multiplier goes up, and that's going to make the IS curve flatter. Mathematically, we worked out that the slope is 1 minus c of y minus t plus I of y over I of I. This is less than 1 by assumption, so again, as this goes up, that gets smaller, and the IS curve gets flatter. I don't actually do it that way, but just a check. And that's d, di, dy from that equation. You have to implicitly differentiate and solve for dy. What we did then was to derive the IS curve under two different assumptions. So we said, okay, let's do one case where c of y minus t is small, and another case where c of y minus t is big. So this expenditure function, what the book calls z, which is c of y minus t plus I of I plus g, this thing gets steeper when the MPC gets larger. So we can imagine c C of y minus t smaller. So that's that case. We can imagine another case, c equals the same thing, and this is z for c of y minus t larger. So the 45-degree line. Now in both cases, we're going to start here at I0. And at I0, in both cases, we get Y0. They intersect right there. So we're starting here at this point at Y0 and I0. Then we lower the interest rate to I1. That shifts both of these curves up by the same amount. We lower the interest rate, investment goes up, both curves shift up. They shift up parallel exactly. So you either get a flat one, that's that case, or a steeper one, that's that case. Oh, good. This is a bit weird. So this one is this line. This is y for c of y minus t smaller, right? Do you see that? Is that too sloppy to see? You don't need to break out the color chalk and pull up at all. And here's what intersects. That's that one, shifting up. That's y for c of y minus t larger. So then we just bring those down. Okay, we've got the same interest rate change, either get to there or there. So we've got this y, this y. This is the big one, the small one, same thing. I just get right at the bottom of the board. So you either get that IS curve or that IS curve. And that's the one for c of y minus t larger. Is that okay? So you have a flat one and a steeper one. That's the steeper case. That's the steeper case there. So that gives you the this is the flatter case here. So you always do these the same way. When you want to know if a curve is flatter or steeper, let's take a step back. So how do we derive that thing? Let's derive it under two different assumptions. Start at exactly the same spot, and then derive it twice. Once for the thing big and once for the thing small.
Why did you shift it up as opposed to the right? When the I changes, it's to the right, and then we'll see if y minus t changes.
Actually, when I changes, you get two different size shifts. You're thinking of something else. You know, I'll come to that in a second. Shift in this direction depends upon the MPC, so it's different. Shift in this direction doesn't. So you get an identical shift in that direction. What else can we say about this? Not a lot. What you're thinking of is, suppose I have two different IS curves. This could be either a larger C of y minus t or a larger I of I. Technically, that's negative. By larger, I configure an adjective. You can shift this point of intersection either vertically or horizontally. And it matters why the two IS curves are different, which way you shift the two. It's C of y minus t. The shift in this direction depends upon C of y minus t, but not I of I. The shift in this direction depends upon I of I, but not C of y minus t. In fact, this shift is 1 over 1 minus C of y minus shift. That was minus 1 over 1 over I of I mathematically. That part. So suppose we have this case, that we have two different IS curves. And this one is flatter only because C of y minus t is bigger. Both have the same I of I. In that case, you would shift the thing. Notice the shift in this direction depends upon C of y minus t. So they're going to shift a different amount in this direction. But in this direction, it does not depend upon C minus t. Excuse me, I got this back. Yeah, this doesn't depend upon C minus t. It only depends upon I, but they have the same I of I. So they're going to shift the same in this direction. So in this case, you would take this point of intersection and you would shift it vertically to there and there. Now, if you have the other case, that you have this case, where it's only because of a larger I of I, then you shift the point of intersection horizontally. And the way to remember this, and it works always, is if it's an I parameter, shift in the Y direction. So if it's I of I or L of I, it goes in the Y direction. It goes opposite. If it's a Y parameter, L of Y and other in the IS curve, C of Y minus T, anything like that, I of Y, it will do that. Then it would shift vertically, shift in the I direction. So you always shift opposite of whatever that parameter is. I didn't do it, but if I of Y goes up, it gets flatter. So the only reason these differed was I of Y, shift it in that direction, in the I direction. Always the opposite. So if you have two different LM curves, I need to do something. Suppose you have two different LM curves, and this is for a larger LY. The only reason it's flatter, DI, DY, I, yeah. The only reason it's flatter is because L of I is bigger. That's an I parameter, L of I, an I thing. So we shifted in the Y direction. So we shifted these two curves, we shift them out horizontal. That's supposed to be parallel. And drop parallel. So we shift this out exactly parallel. So it's always opposite of whatever is causing the change. Remember that. gave a problem like this to my graduate students, about half of them got it wrong. It's sort of a tough thing. Then I told them about half of you got it right. Embarrassing. This comes up doing policy effectiveness. So the context here is monetary policy more or less effective when L of I is bigger, C of Y minus T is bigger, I of I is bigger, things like that. So that was the context we did these policy effectiveness. Does that answer it?
Yeah.
You have IS. You want to know how it shifts? You can either look at, suppose that government spending goes up, and I want to know how the IS curve shifts. I can find dy dg given di equals 0. That's this one, that's the horizontal. That'll be 1 over 1 minus c of y minus t plus I of y. So the horizontal shift does not depend upon I of I at all. The shift in this direction will be minus 1 over I think. Yeah, minus 1 over I of I. So in this direction, it doesn't depend upon C of Y minus T at all. Mathematically, if you work it out, this one here is DI DG given DY equals 0. So you hold Y constant, shift in this direction. So mathematically, you want to know how a curve shifts. You hold one of the variables constant, look at the horizontal and vertical. It doesn't matter which way. What's important here is the vertical, because I is held constant, will never depend upon I of I di, because di is 0. So the horizontal shift can't depend upon the I of I parameter, because you're holding I constant. The vertical shift can't depend upon C of Y minus T, because you're holding that constant. I'm just waiting for some of the questions. Any other questions? Okay, good.
It's not on this portion, but.
That's fine.
Can you explain the golden rule graphically?
Sure. Explain the golden rule graphically, please. Well, I didn't do that. Honestly. That was just a bad recitation of the question. Okay. Basically what you do is you make an argument when S equals 0, when S equals 1, output would be 0, and consumption would be 0. So in this model, output is a function, output per person is a function of capital per person. If S equals 0 forever, K equals 0, Y equals 0, so C equals 0. So when the savings rate equals 0, you never got any capital because you're always consuming. When you never have capital, you don't have the output of this model. So you need capital to produce output. So when S equals 0, it must be, so if we were to graph consumption and S, we know that S equals 0 means consumption equals 0. Now when S equals 1, it's all investment and no consumption. It's not really a sustainable economy because nobody's eating. You're using all of your resources to produce capital. Investment is 100% of output. So consumption is 0. Output is consumption plus investment plus government spending. We just shut down the government this problem. So So essentially, output is C plus I. If I equals Y, so we know that Y equals C plus I plus G, but for this one, we're just making that 0 to make it simple. We're holding it constant. So if I is 100% of output, if I equals Y, C equals 0. So when S equals 1, C equals 0. Now we already know that in between, say when this is 50%, consumption is non-zero. So you just make a continuity argument, okay, that it must be that it looks something like this. Because we know its consumption is non-zero in between, and it's a continuity argument. So as S goes up, consumption goes up for a while. And this then is the golden rule level of savings. And they're actually doing this C over N. Makes no difference, N is fixed here. And then the other part of the question asks, when we looked at the data, we didn't take a close hard look at this class. But when people look at the data, it appears like savings rates are below the golden rule. And then we ask, why would it be that the savings rate would be below the golden rule if that maximizes consumption? And then we made a political economy argument that when S goes up, when you're to the left, when S goes up, that causes consumption to go down in the short run because you're investing more, so you're consuming less. So today's people would have to give up some consumption, but it makes consumption go up in the long run. So your kids and their grandkids will be better off. Then, I didn't really ask about this, I rolled it over whether I should, but I thought it was kind of too hard to really ask as a review question. But we made an argument based upon a specific form of the model that this probably takes about, even after 10 years, you're only 40% for the new long run. So this could take easily, 20, 30 years for the long run effect to show up. So, I'm 56. I'm thinking, okay, if I vote for this when I'm 86, my consumption will be higher. I don't think I want to give up. And old people vote a lot. I don't think I want to give up a lot for you guys. I'm sorry, you don't vote very much. Just kidding. So, this generation is not willing to give up consumption in the short run to live closer to the golden rule. That's the argument that's generally made about why we are, for the most part, below that peak. This should maximize utility in the long run, because utility is a function of consumption. It's a function of the stuff you eat. It's not a function of how much you invest. In the end, you care about what you consume, so your standard of living. So, that would also maximize the standard of living. So we took a rather non-analytic, well, this is the key. S equals 0, S equals 1. And we know it's non-zero in the middle, so there must be a maximum. We'll start doing math, you can ask questions. I'm kidding, okay?
No.
I could see you were doing that. I do that.
show how the steady state for K over N environment graphically for the steady state?
Say it again.
Can you show the steady state for K over N environment, Y over N graphically?
Which model? The with or without population, and is this 1 through 6 or 7 through 12?
1 through 6.
Okay, so this is the chapter 11 model. In the chapter 11 model, N is fixed, there's no population growth, and technological progress is fixed. There's no A. Okay, that's right. I knew that, because the other one would have been Y over A. So I said show it graphically.
And explain why the steady state is equilibrium.
Okay, gotcha. So the equilibrium condition here, where delta k t plus 1 over n equals 0, is where delta k equals delta k over n equals sf of k over n. This is sy. This is little sy. This is investment. This is new capital. This is the capital we lose. So the steady state is where the new capital in the economy is exactly equal to the capital you lose from depreciation. So the steady state is simply a matter of finding the point where those two things are equal. So we'll just graph these. There's k over n. Delta k over n is just a straight line out of the origin. That's what that line is. So there's delta k over n. So this is a steady state because this is where the change in capital is equal to 0. We had a capital evolution equation that said kt plus 1 equals it minus delta kt. And then that turns into this condition. This is all on pages this is about page 230, is what I'm doing right now. Where this condition comes from, let me back up. The capital at t plus 1 is 1 minus delta times the capital at t plus the investment at t. Investment equals savings. Savings equals sy. We'll come back to that. So I can say kt plus 1 is 1 minus delta kt plus syt. So what does this say? It says, okay, the capital tomorrow will be the capital today that didn't depreciate. So this is what's left over after depreciation. Delta k is the depreciation part. 1 minus delta is the part that sticks around, that survives. So the capital tomorrow is what's left over after depreciation, plus the new stuff. Now we can just divide by n, because that's what we do. We want it to be in per person terms. Then you can move one of these to the other side. So kt plus 1 over n minus kt over n. So I'm just taking part of this to the other side. Is minus delta kt over n plus sf of kt over n. This is yt over n. So that's that term. That's that term. I split this term into two pieces, move that part to the other side. This is the change in capital. That's what I was talking about here. For that to be 0, that plus that has to be equal to 0. And the way that is 0, so this is 0 when that. Because if those two things are equal, they'll cancel. So this is the condition that keeps k over n constant through time. The change in capital is 0 in every time frame. So we just need to find that point. Well, here's SF of kt over n. That's where they're equal. That's the steady state for capital and labor. Capital per person, per worker. Sheets are squeaky today. Stop tasting. Get some dust on. You must have swept the floors. Let me clear some clutter out. And we need to find output per worker. S is a fraction. This is y. So there's another line here that's f of k to r. S is like 1/3. So I didn't draw it very well, but this is 1/3 of that. Some fraction of y goes to savings. The rest goes to consumption. So if we just take this line up to here, that gives us y star over n. I didn't put a t on these because they're steady. They're the same at every point in time. So that's just the steady state. Now we need to make the argument. The second part of the question is, show that the steady state is in equilibrium. There's a natural tendency for the economy to go to this point. To do that, we consider a point above or below equilibrium. So suppose we're at kt over n naught. Has it always done that and I just didn't notice? Maybe I was just quiet. It's like when you're at a basketball game, you can like soak your badge into the sweep. Suppose we're here. If I put k over n here, what am I getting? Delta k over n. What's delta k over n? That's the depreciation or the loss of k, right? So that's how much capital we're losing. What's this point right here? Investment. So that's the new k over n. So what's bigger, the part we're losing or the part we're gaining? So we're gaining more than we are losing here, right? Therefore, it must be that this is moving in that direction. So if we're down here, there's a tendency to move towards a steady state. Now, if we were over here, that would be the new, and this would be the loss. Here, you're losing more than you're gaining. So k over n must be falling. So wherever you are, you're going to move over time to the steady state. So it's an equilibrium. The other model, I asked exactly the same question in questions 7 through 12. What question was that? 9. Yeah, so number 9 is exactly the same question, except it's with technology. And this is delta plus GN plus GA. Okay. But it's exactly the same setup, you just have a different, I can go through that one if you want. If it turns out to be the same picture, you just have AN on the bottom instead of N, and you have a little bit different function there.
I have a question. What's considered between output and investment? What is that area?
Consumption.
Consumption.
Oh, I'm here?
Yeah, I think that's what it is, right?
Yes. In this model, there is no government. We can add it, y equals c plus I. So once I know I and y, c is the difference. And this is equal to s. So y minus s or y minus I is equal to c. So that difference is in fact exactly what it is. In the second model, we need to leave k over an constant. In the first model, we just did it was k over n, and n was fixed. So k didn't have to change at all for n, because n was fixed. So the only reason we lost capital, we had to change the capital stock to keep it constant, was to compensate for depreciation. So depreciation, so in that model, we just had, okay, S, F of k over n, investment equals delta k over n, depreciation. The gain equals the loss. In the model where we have n growing in technological progress, so this grows at Gn. This grows at An. GA. It's there somewhere, some combination of GA and N. We'll get it. So now to keep K over AN constant, there's 3 things we have to compensate for, right? First of all, K is going to fall by what? The depreciation rate. So we're going to need a delta K over N term. Again, that's going to be part of what we're going to have. K is going to have to grow by that just to compensate for the top part, depreciate. But K over N is going to have to grow by even more this time because it also has to compensate for A going up and N going up. We want this to stay constant. Suppose there was no depreciation at all. K would have to grow by the rate this grows and the rate this grows. Otherwise, if it didn't change at all, there was no depreciation, K was constant, A and N are growing, that ratio would fall over time. That's not what we want. We want it constant. So it has to grow also by Gn plus Ga. So that's the amount that we have to increase the capital each period in order to keep K over N constant, K over AN constant. This is this falling. You have to build it back up. And this is the part that keeps the ratio constant when these grow. So our investment in this case has to compensate for 3 things. Oops. You can get rid of the ends if you want. All right. These should be ANs. I'm sorry. Yeah, that's how they wrote it. You see that argument? Apparently. No, you're so lost you can ask a question and it's so easy, you got it.
So that's the steady state.
That's the condition for the steady state. So this is the new, this is essentially the loss. It's not- This is the loss, this is the part that this grows.
Which is just decreasing the rate at which.
Well, this is A growing over time. We could put T's on all these things. For some reason, the book decided to drop the T's in chapter 12, but they have it in chapter 11. I don't know why. So AT is growing over time at rate GA. Today it's 10, tomorrow it's 12, the next day it's 14, 16. It's not quite a constant growth rate, but you get what I'm saying. If this isn't growing at the same rate, that ratio will decline. We want the condition for that ratio to be constant. So this has to grow at the rate that A grows. K over AN has to compensate for that. So that's this part. And then N is also growing population. So K, if you want to keep K over AN constant, it has to grow by rate N. And this is the depreciation.
You said to keep it constant for everything and everything.
Yes. I don't know if this will help or not. Let me show you something. If you have K over AN, the percentage change in K over AN would be the percentage change in K minus the percentage change in A minus the percentage change in N. So mathematically, that's just true. This is the depreciation part. This is G of A. This is G of N. And this is minus, this is delta K. Delta. So we have to keep this constant, we have to compensate for all three of those things. Hmm?
And how about the population increase in the savings rate?
Okay. So this, you can see that this goes up. So the steady state in this case is delta plus GA plus GN times K over AN. This axis is K over AN. This axis is Y over AN. And this is S0 F of K over AN. That gives you the steady state. Then we put the production function on there. F of K over AN. And that gives us Y over AN. That's the initial steady state. Let me put zeros on those. Then if you increase the savings rate, say to S1, that's going to give you a new steady state level of capital per effective worker, and effective workers, and a new steady state.
You said it gives you capital effective workers?
Right here. Capital per effective worker goes up. So you'll get growth for a while until you reach the new steady state. So an increase in savings will cause you to increase the standard of living from one steady state to another. And as you move between steady states, you'll get growth, but you won't get a long run change in growth, or you won't get a steady growth in the standard of living. Y over A, in this model, you won't get a steady growth in Y over AN. Y over AN will go up for a while. This could take 10, 15, 20, 30 years, but eventually you'll top off and get a new steady state. So you don't get a permanent growth in output per effective worker. You get a spurt of growth for a while, then you hit the new steady state. But, to go on to another question, in this model you do get growth in Y over N.
So in the previous model, there would be a permanent change?
What's that?
So in the previous model, when it was Y over N instead of Y over N, it would be different?
Yeah, because in that model, Y over N doesn't grow permanently. In this model, if you work it out, Y over N grows at the rate of technological progress. So in this model, the growth, I haven't shown this yet, of Y over N is equal to GA. In chapter 11, G of A was equal to 0. So you could get a change in the standard of living from steady state to steady state, but you never got a permanent increase in the standard of living. So in the last model, I think this is Y over N. So Y over N would go up, but then it would hit a new level and would stop. In this model, Y over N grows forever, and it grows at the rate G of A. So if you can increase the rate of technological progress, not only do you get a constant increase in the standard of living equal to the rate of technological progress, but you can get even larger increases with even faster rate. This is the rate of growth in technological progress.
So we shifted the rate of growth one year. We shifted the savings line.
Right.
The growth line, right?
Well, no matter where you're at, you'll get that the rate YN grows here or here at that rate. So you can show that, this is all on page, where is it? Can you find it? Can I tell you where to look? Yeah, this is page 254 about. See, in the steady state, Y over AN is constant, right? That's what the steady state means. Y over AN is constant. But A and N are growing, right? These things are growing at rate G of A and G of N. Is that right? That's right. So, what rate does Y have to grow at? If this is going up by 10%, this product, how much does that have to go up to keep it constant? 10%. So it has to grow at the same rate. So the growth of Y is equal to GA plus GM. That's the only way that can stay constant. Now the growth of Y over N equals the growth of Y minus the growth of N. The growth of A over B is the growth of A minus the growth of B. That's just a mathematical result. When they're When they're multiplied, you add them, just like logs. And when they're divided, you subtract. The growth of y is GA plus GN, and this is GN. So the growth of y over n is GN. So to get that result, you don't need a graph or anything. You say at the steady state, y over an must grow at that rate. Otherwise, that couldn't be constant. You want the growth of y minus the growth of a minus the growth of n to be 0. So that's what that says. The growth of y minus the growth of a minus the growth of n equals 0. Then you say, okay, what's the growth of y over n? Well, it's the growth of y, which is GA plus GN, minus the growth of n, which is GN.
So the question is, any reason that does cover big growth now, but
It doesn't change the growth rate of output if G of n goes up, of y over n. And it doesn't, this does not depend upon S, this does not depend upon, S or G of n.
so when you shifted S, they did not cause.
That doesn't change the that doesn't change the growth rate of y over n. It changes the standard of living. What happens is, here's y over n over time, and it's growing at one rate. Say it's growing that fast. Then you increase the savings rate. That increases y over n to a new level. So it jumps it up. But you grow at exactly the same rate from then on. So when S goes up, it does raise the standard of living, but it doesn't change the underlying growth rate
It gives a permanent increase.
in the level. So you're growing from a higher level. So when I moved up to the higher y over n, when y over an, you're growing from a higher level, but the growth rate itself hasn't changed. See that? And the book process is, well, it takes time. It does. I jumped it up immediately, but that's. These are supposed to be parallel, whether I drew it that way or not.
And that's true for what Y rate, Y rate.
This is just y over n. Y over an doesn't grow. Y over an looks like this. It's at a steady state, and it jumps to a higher steady state, but it's steady, it doesn't grow. But y over n does. The graph has k over an and y over an. So when you get the steady state, it's a steady y over an, so it doesn't grow. Basically, if A is growing, y over n has to grow to compensate. That's all that's going on here. A is going up, y over n has to go up by the same rate to compensate. So y over n has to grow at the rate of A. Keep that ratio constant. That's all that's going on. So in the first model, y over n does not ever grow, because g of a is 0. The point was, with technological progress, we can get permanent growth in the standard. That is my question, I think. The growth, you don't have to know this, is the change in x over x. x goes from 100 to 110. It's 10 over 100, it's 10%. So the change in x would be 10 over the, depends on which endpoint you use. We usually use the starting point, you grew from that. So x goes from 100 to 110, this would be 10 over 100. So the way to find the growth rate is d log x, which is dx over x. So if I want the growth rate of xy, I can just say d log xy, which is d log x plus d log y. So it's dx over x plus dy over y. So the growth of the product is a sum. That's how you get that result. Anyone cares. It's like what, 25 outside or more?
Previous model of wire brand is pretty similar with the appreciation curve shifts.
So, delta 0. This is chapter 11, so there's no A. It's, F. And there's your initial steady state. The question is, what happens if depreciation goes up? So this curve would do what? It would get steeper, right? So this curve would rotate upward, and you would end up at a new steady state. Okay, we're at 1. And y. So this point.
So when we say technology is the reason why the standard of living goes up, but does the saving rate actually have an effect on the standard of living? Because
Yes.
Because doesn't it fluctuate so much based on like policy changes that in the long run it wouldn't even be constant enough because it takes so long to go into effect, or to have an effect, I should say?
So you might think that, imagine driving a great big ship in the ocean, and the captain's whipping the wheel around. It's, yeah,
Gotcha. Okay.
that's how it's going to come out.
Okay.
And if you keep it in one direction long enough,
Right.
it'll move the ship.
Gotcha. Okay.
I gotta stop these.
Did we incorporate any of the dimension returns when we're talking about the y over AN?
Yeah. So we start off with y with some function of k and a. We said, let's take a special form because it's better to work with. We said y is some function of k times an, so we just took the product rather than taking them individually. Then we said, suppose there's constant returns to, now each one of these, we have constant returns to scale. So if we double all of these, we double output. We have diminishing returns to individual factors. So if k goes up with n and a constant, we get diminishing returns. If n goes up with all else constant, we get diminishing returns. If a goes up, all else constant, you get diminishing returns. With constant returns to scale, we can divide by an. So you say, okay, well, y, this is actually one of the problems too, I think. is f of k over an and 1. And we've just been writing that as a little f of k over an. When you graph that, it looks like this. So here's k over an and y over an. I'm graphing this curve right here, but with technology. So f looks like this. There's f of k over an. The fact that this is getting flatter and flatter and flatter means that that's diminishing returns. So it has diminishing returns in k over an. Down here, when we increase output by a chalk length, or increase k over an by a chalk length, we get a pretty big increase in output. Way out here, if I increase by a chalk length, from there to say there, I don't get much of a change in output at all. So the returns to that amount of an increase in k over n are diminishing as we move along this. So we have diminishing returns to individual factors, constant returns to scale. We scale everything up, then we double stuff.
What exactly you be asking us to respond to this?
Just derive the production function. I can't remember what question I asked.
Maybe like, so like,
Should be like 7.
constant return scale or something?
Yeah, yeah. What's it say?
Like, what it is, take the collection of progress and actually incorporate it.
Yeah, this is how you can incorporate it. I didn't ask about diminishing returns though. It's not good to yawn in front of your class.
How about, where are the, for development?
Okay. So the end of chapter 12 basically tries to make the following point. There's 2 ways for economies to grow. One is that we know that the growth of y over n equals g of a. So we just worked that out. So that's one way you can grow. The other way you could grow is if you were a country, let me use the more general model, delta plus GA plus GN so k over AN. And here's S, F, and K over AN. And this is the steady state, K over AN. And we're way down here, like you might be in a developing country. As you move to the steady state, the standard of living will grow over time. So one way to grow is through technological progress. The other is you're below the steady state and you get capital accumulation. So if you have a very low level of capital relative to your steady state, as you might think a developing country would, the growth may be through capital accumulation. If you're at the steady state, like a developed country might be, or near it, then the growth might be more through GPA. So it could be either. Y over N could be going up for either reason. So which reason is it? Well, we looked at some data for developing countries, developed countries, and we saw that the rate of growth of Y over N, the standard of living, looked pretty close to the rate of growth in technology, somehow measured. So for developed countries, it looks like growth is due to technological progress rather than capital accumulation. But when you look at developing countries, they tend to be down here. And so their growth tends to be more from the accumulation of capital, moving towards the steady state, rather than being at the steady state and growing at the rate of technological progress. They can grow for both reasons. They can have both technological progress and capital accumulation going on at the same time. But for developing countries, it seems to be much more related to the rate of capital accumulation than it is to the rate of technological progress. It's just the opposite. A is growth. That's what we're going to do.
Do you maybe do price of oil problems with the same instrument? Yeah, like a growth in the price of oil.
Yeah.
Like IS is telling it in the other.
Yes.
맞습니다. 그거는 특별한 사람 말고 그 나머지 사람들은 그 정도 뭐 하는 거지? 처음에 좀 좋아하는 거.
So this was a question about the question on the second midterm about what happens when there's an increase in the price of oil. Now, the thing to remember is the price of oil is a supply shock. And it changes the natural rate of output. And so an increase in the price of oil shifts both the long run and the short run supply curves back simultaneously. So when the price of oil goes up, both the long run supply curve and the short run supply curve both shift back. Expectations didn't change. We're still at this point. And so they both shift. And we started at this point A, P equals P0. In the short run, we'll move up here to point A to where the demand hits the short run supply curve. So the short run will move from A to B. Now that causes P to go up to P short, causing output to go to Y short. So let's find that point down here. Y short. So we know we must be on right there. So the LM curve shifts back LM and over PSR. Now this economy is overheated because here's the new long, medium run equilibrium. We're above it. So that will cause the short run supply curve to begin doing what? Shifting back. So this thing will start shifting back until we get point C, P medium run, P1 call it. So this is the short run AS. PE equals P1. So as those price expectations rise, we move here to point C. Let's find that down here. Okay, well there's Y1. It must be that the LM curve shifted back to LM and over P1. So there's A, B. And that's your new long-run equilibrium, is a lower level of output and a higher level of price. That intervening period when output's falling and prices are, and they have inflation is called stagflation. No one really talks much about stagflation anymore. It's drawn much better in your book. Somewhere. Page 151. That only has the aggregate demand part of it, but oh well. Just have to sit and wait. So, okay, I'll ask a question. Then you wait long enough, you say, okay, I guess they're done. Any of the free riders have a question? Two types of people that come in here. There's the ones with the questions and there's the free riders. There's one with the material and one. Sometimes you get so many free riders and no one asks anything. That's okay. I guess we're done.